Let us compare the rate of a chemical reaction to that of an enzyme-catalyzed reaction. Enzymes can enhance the rate of a reaction by factors of 10 to the power of 7 to 10 to the power of 15, accomplishing in 1 second what would otherwise take 300 to 30,000 years in the absence of an enzyme. How do enzymes accomplish this? Under physiological conditions, chemical or non-catalyzed reactions occur slowly and require high activation energy. Consequently, these reactions display little or no specificity for their reactants. Consider the hydrolysis of one of the most common biological macromolecules, such as DNA. The hydrolysis of the phosphodiester bond in DNA is extremely slow under normal physiological conditions. This is one of the reasons DNA is such a stable genetic material. On the right-hand side of the screen is a diagram showing the rate constant and the corresponding half-life. The rate constant and half-life are related by the equation T and a half is equal to 0.693 divided by rate constant K. The rate constant for spontaneous hydrolysis of the phosphodiester bond in the DNA backbone has been measured to be approximately 10 to the power of negative 13 to 10 to the power of negative 15 per second, which corresponds to a half-life of about 30 million years. Another closely related to DNA molecule is RNA. The rate constant hydrolysis of the phosphodiester bond in RNA is approximately 10 to the power of negative 10 to negative 11 per second, which corresponds to a half-life of 4 years. Compared to DNA, the hydrolysis of the phosphodiester bond in RNA occurs at a faster rate because of the 2' hydroxyl group, which acts as an internal nucleophile that attacks the adjacent phosphate. The uncatalyzed hydrolysis of a peptide bond in proteins has a half-life of roughly 500 years, whereas that of a glycosidic bond has a half-life of about 12 million years. In its presence, enzyme can enhance the rate of a reaction by factors of 10 to the power of 7 to 10 to the power of 15, accomplishing in 1 second what would otherwise take hundreds of millions of years in the absence of an enzyme. But before discussing how enzymes accelerate the rate of a chemical reaction, it is important to examine 2 key factors governing chemical reactions: thermodynamics and kinetics. Thermodynamics is concerned with how favorable a chemical reaction is. It focuses on the Gibbs free energy change, or delta G, of a reaction and determines whether the reaction occurs spontaneously. Kinetics, however, deals with the rate of reactions. How fast wills the reaction occurs. It deals with the activation energy rather than the delta G. Thermodynamics and kinetics describe 2 different aspects of a chemical reaction. Consider the following reaction, where A is converted into B and C. If the products B and C are more stable than A, the equilibrium will lie toward formation of B and C, making the reaction thermodynamically favorable and resulting in a negative delta G. In contrast, kinetics focuses on individual rate constants, such as K1 and K-1, rather than on the equilibrium constant, which is defined as the ratio of K1 to K-1. It is possible to have a reaction that is thermodynamically favorable and has a negative delta G. Yet, this reaction may have slow kinetics and therefore occur very slowly. Consider the hydrolysis of ADP to ADP, an inorganic phosphate in the absence of an enzyme, a reaction that is thermodynamically favorable but kinetically slow. In the diagram below, the x-axis represents the reaction coordinate, whereas the y-axis represents the potential energy. If one compares the potential energy of ADP with that of ADP, an inorganic phosphate in the diagram, ADP and inorganic phosphate have lower potential energy and are therefore more stable than ADP. The Gibbs free energy change, or delta G, for this reaction is minus 30.5 kilojoule per mole. Therefore, this reaction is thermodynamically favorable and occurs spontaneously. However, anyone who has prepared a stock solution of ADP knows that the solution is quite stable and can be stored in a refrigerator for months without significant degradation to ADP, an inorganic phosphate. This is because although the reaction is thermodynamically favorable, it is kinetically slow. In other words, the reaction is prevented from occurring rapidly due to a high kinetic or activation energy barrier. According to transition state theory, for a reactant to be converted into product, it must pass through a highly unstable, transient structure known as the transition state. The transition state structure is highly energetic, unstable, and has a very short half-life, on the order of picoseconds. At the present, since no instrument is capable of directly measuring the transition state, its structure is postulated rather than directly observed. This is because at the transition state, existing bonds are being broken or partially broken, while new bonds are being formed or partially formed. To be converted into product, the reactant must possess enough energy to climb over this barrier, known as the activation energy barrier. Thus, although the hydrolysis of ADP is a thermodynamically favorable reaction because it has a negative delta G, it proceeds at a very slow rate due to the high activation energy barrier. This leads us back to the original question of how an enzyme accelerates the rate of a reaction. The several ways in which enzymes accelerate reactions are as follows. First is the transition state stabilization. The second way enzymes accelerate reactions is through the proximity and orientation effect. The third mechanism is by general acid and general base catalysis. The fourth is through covalent catalysis. The fifth is metal ion catalysis. Compared with the other catalytic mechanisms listed here, transition state stabilization is perhaps the most important and will be discussed first. Consider the following diagram, in which substrate S is hydrolyzed into products P and Q. In a non-catalyzed reaction, the covalent bond between P and Q is broken or partially broken, leading to charge separation in the transition state. Because the transition state formed in this reaction has significant ionic character and is highly unstable, the activation energy barrier is high. In its presence, the enzyme lowers the activation energy of a reaction by binding tightly to the transition state and thereby stabilizing it. Note that the overall free energy change, delta G, of the reaction is not altered by the enzyme. One can think of an enzyme as a receptor that binds tightly to the transition state, not the substrate. Tight binding of the substrate, in principle, is anti-catalytic because it stabilizes the ES complex and therefore increases the activation energy. The more tightly an enzyme binds to the transition state, the greater the rate enhancement achieved. Tight binding of the transition state by the enzyme is accomplished by having an active site that is structurally complementary to the transition state. For example, assume that a cationic transition state with a positive charge is formed in the reaction due to cleavage of a chemical bond in the substrate. To be structurally complementary to this transition state, the enzyme's active site must possess a negatively charged amino acid side chain residue to stabilize the cationic transition state. Similarly, if this part of the transition state is hydrophobic, the enzyme's active site must also contain a hydrophobic side chain to allow hydrophobic interactions. If this part of the transition state contains a hydrogen donor group, the active site must contain a hydrogen bond acceptor. Linus Pauling proposed that an ideal enzyme is one whose active site is complementary to the transition state rather than the substrate. Despite the structural similarity between the substrate and the transition state, the enzyme must discriminate between them and bind preferentially to the transition state. An analogy is the game where one is asked to spot minor differences between two very similar pictures. A real example is the deamination of adenosine to inosine by adenosine deaminase, which proceeds through the formation of a hypothetical tetrahedral transition state. In this reaction, a tetrahedral transition state is formed by the addition of an OH group from a water molecule to the C6 position of the purine ring. Inosine is subsequently formed by the elimination of ammonia from the transition state. Because a tetrahedral geometry at the C6 position of the purine ring is a unique feature of the transition state, and the enzyme must selectively bind to it. Purine riboside analogs whose structures contain a tetrahedral carbon at C6 bind tightly to the enzyme. In fact, purine riboside analog and cofomycin, whose structure mimics the tetrahedral transition state, binds to adenosine deaminase several million times more tightly than its natural substrate, adenosine. Note that both of these analogs lacks the amino group, and therefore the deamination reaction cannot occur. This observation gives rise to the concept of transition state inhibitor. In principle, to design a potent enzyme inhibitor, its structure should resemble the transition state rather than the substrate. To summarize the concept of transition state stabilization, enzymes accelerate reaction rates by binding tightly to the transition state. This stabilization is achieved because the enzyme's active site is complementary to the structure of the transition state formed during the reaction. The higher the enzyme's affinity for the transition state, the lower the activation energy.